make a quick video about examples of problems that we've been doing in this chapter and things to work on. Reference angles, I'm sorry, first I'm going to do converting between degrees and radians. 210 degrees, well if it's on your unit circle, and 210 degrees is on unit circle, the degree measure is very quick to find. 210 just goes to 7 pi over 6. So the degree measure here is 7 pi over 6 radians. And 55 degrees, well 55 isn't on the unit circle. We know it's going to be somewhere in here. Somewhere in there is 55 degrees between pi over 4 and pi over 3. But when it's not on the unit circle, you have to do your conversion. I'm going to multiply by pi over 180. And most numbers can reduce with 180, so they usually simplify pretty well. Don't make this a decimal, but actually reduce. So 55 over 180, if you want to find that reduced in your fraction, 55 divided by 180 gives you that decimal. Press your math button and arrow frac. It's 11 pi over 36. So 55 degrees is 11 pi over 36 radians, which is about a third of a radian. I'm sorry, a third pi radians, which is, right around pi over 3. Other way around, 5 pi over 4, again, if it's on the unit circle, and this one is, it's 225 degrees. If it's not on the unit circle, I'm going to have to convert. So I do times 180 over pi. The nice thing is the pi's cancel. 3 over 180 becomes a 60, so it's 7 times 60, which is 420 degrees. And 420 degrees is more than one circle, because 7 pi over 3 is more than one circle. So we would take that, and if we wanted to, turn it to 60 degrees, because that's one extra revolution. So it turns out 7 pi over 3 really was on the unit circle. I mean, think about pi over 3. There's 1 pi over 3, 2 pi over 3, 3 pi over 3. Excuse me. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3. 7 pi over 3 is the same as 60 degrees. That's radians to degrees or vice versa. Reference angles is another one we're going to look at. A reference angle is just taking an angle and putting it in the first quadrant. So the first example we have is 210 degrees. Well, again, if things are on the unit circle, they're always easier. 210 degrees is right here. This angle here is 210 degrees. And basically, the reference angle on the unit circle is just take this point and find its corresponding point here. If I think about drawing this rectangle from this point all the way through, all three of these points here, this one, and this one, they all share the same reference angle of pi over 6 radians, or 30 degrees. So the reference angle is 30 degrees. The point of a reference angle is that the x values are the same, plus or minus, and the y values are the same, plus or minus, positive or negative. So it could be 210 degrees is 30 degrees for the reference angle. Now 500 isn't on the unit circle. And specifically, 500 is more than a whole circle around. 500, what is going on? Anyways, I'm going to get rid of this rectangle. 500 degrees is a whole circle plus 140. So we're really sitting here at 140 degrees. Well, a reference angle is just the angle to the x-axis. Always the angle to the x-axis. So that's 140, then this is 40 degrees. So the reference angle is 40 degrees. And we said this one was 60. Negative 100. Well, negative 100 is here. This distance right here was negative 100, which means that this distance here is 80. I keep saying distance, it's really degree. That angle is 80. So the reference angle there is 80 degrees. It's always just the angle to the x-axis, not the angle to the next axis or to the y-axis, always to the x-axis. Radians are tougher because you're less familiar with them. 5 pi over 3 is here. And so its reference angle, well, 1/2 happens here for x, 1/2 happens here for y. So its reference angle is pi over 3. I'm going to erase all this now. 6 pi over 7. Well, pi over 7s aren't on the unit circle. So I have to think, well, where is 6 pi over 7? If you wanted to, you could convert that to degrees and do it in degrees and then convert back into radians, that's a fine option. But I think about 6 pi over 7, it's less than 1 whole pi, so it's going to be like here. That's about 6 pi over 7, because I know that 7 pi over 7, or just pi, is 180 degrees, or half a circle. So if that's 6 pi over 7, then this leftover piece here must just be 1 pi over 7. So this is going to be pi over 7 radians. And what you can do is take your x-axis, which in this case is pi, and take away the extra stuff. So pi minus 6 pi over 7, I need to get a common denominator, and that gives me pi over 7. Negative 13 pi over 4. Well, sometimes just knowing where that is can be challenging. So I'm going to count by pi over 4s for a while. Here's a negative 1 pi over 4, negative 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6, 7, 8, 9, 10, 11, 12, 13. There's a negative 13 pi over 4. Well, negative 13 pi over 4 is the same as 3 pi over 4, and 3 pi over 4 here means that this leftover part right here is pi over 4. It corresponds to an angle of pi over 4 radians. I think I'd like to do a couple more just to make sure we can handle all of them. So let's talk about let's do 9 pi over 11. 9 pi over 11 is more than 1 pi. I'm sorry, it's less than 1 pi. I just want to flip it around. I'm going to do 11 pi over 9. 11 pi over 9 is more than a whole pi. So I'm somewhere in here. I don't know where, but somewhere in here. I'm less than 1.5. And basically you have to check your quadrantial angles. 1.5 pi would be here, but 11 over 9 isn't quite 1.5, so I'm in quadrant 3, not in quadrant 4. Since I'm in quadrant 3, my question is, what's this angle here? Well, now I can just take away all this extra stuff. If I take away this extra 180 that I have, if I take away a pi, I need to get a common denominator. It's 2 pi over 9. So this angle here is 2 pi over 9. That's its reference angle. Finally, if I was at some random place in quadrant 4, like say I'm here, and we'll say that's 17 pi over 5. Just some random spot to make up. 17 pi over 5. Well, I'm trying to find this angle here, which means I really want to find, out of 360, what was left. So if I do 2 pi minus 17 pi over 5, that becomes 10 pi. 17 pi over 5 is way too big. So let's just forget this one. I don't want 17 pi over 5, I want... Oh, 17 pi over 5 should work. No, it shouldn't. There we go, 8 pi over 5. What I'm doing is I'm trying to find a decimal that's bigger than 1.5 that isn't on the unit circle. So since 8 divided by 5 is bigger than 1.5, I know I'm bigger than 3 pi over 2, so I have to be in the fourth quadrant, and that's the one quadrant we haven't done yet, so I'm going to play with that. In the fourth quadrant, I want to figure what's left. I basically have this angle right here, from here to here. So I'm thinking, how much of this space was left over? Because I'm always trying to find the angle to the x-axis. So if I do 2 pi minus 8 pi over 5, well, that really becomes 10 pi over 5 minus 8 pi over 5, and that's 2 pi over 5. So there's the reference angle, 2 pi over 5. Okay, moving on. The coordinate of this point P, we've learned a lot of ways to do this, but the simplest way, really, is I just know that cosine is x and sine is y. So if I take the radius of 17, and I do 17 times the cosine of 340, that'll give me the x-coordinate, and 17 times the sine of 340, that'll give me the y-coordinate. I need to make sure they have the right sign. By that I mean positive, negative. Make sure they have the right positive negativeness. I'm going to make sure I'm in degrees also. So that's in degrees, yeah. 17 cosine 340. 15.6. I don't know why I can't write a 6. 17 sine 340. Negative 5.8. Let's make sure those points work. Yep, that makes sense. 15.6, comma, negative 5.8. That puts us in the right, in the correct quadrant, and matches up with the radius here. Good. Next, find theta and the 6 trig ratios given that secant of theta is negative 5 over 2 and you're in quadrant 3. All that quadrant 3 is doing, all that's trying to tell us, is that the cosine will be negative and the sine will be negative, and we'll probably have to play with this theta when we try and find it. Well, if secant of theta is negative 5 over 2, then that means that cosine of theta is negative 2 over 5. So if cosine is negative 2 over 5, I can think about this triangle. Opposite hypotenuse. Cosine is adjacent over hypotenuse, so that's my theta. Here's a negative 2 or a 2. Think of it either way, and that's 5. 5 squared minus negative 2 squared equals our b squared, so 9 minus 4 is 5. So b is the square root of 5. So this length over here is just 4. Oh, did I come out to whole numbers? I'm sorry, I don't know what's happening here. I'm a mess. I'm going to slow down. 5 squared minus negative 2 squared is our b squared. So 25 minus 4 is b squared. So 21 is b squared. So the square root of 21 is b. And that's what we're going to call this length over here. Square root 21. From there, I can get sine, cosine, tangent pretty quick. I've already got cosine. Sine is opposite over adjacent, or opposite over hypotenuse, so root 21 over 5. Tangent is opposite over adjacent. So here's my opposite over my adjacent. So it's negative root 21 over 2. Then I flip all these around. We already knew that secant was negative 5 over 2. Oh, this is going to be negative actually because I'm in quadrant 4, so this is positive. Cosecant, 5 root 21 over 21, and that's negative. And so cotangent is positive 2 root 21 over 21. Now the last question is, what's theta itself? What's the actual angle measure? So I can do a cosine inverse of negative 2 over 5. But this probably won't give me the right angle. In fact, I know it won't give me the right angle because it's in quadrant 3. So the cosine inverse of negative 2 divided by 5 is telling me 113 degrees. Well, 113 degrees would be here, because cosine values always come in quadrants 1 and quadrants 2. Sine values always come in quadrants 1 and quadrants 4. There's no space in your calculator to store quadrant 3 values. So we have to find it. We have to use reference angles, actually. If that's 113 degrees, then this little bit here is 77 degrees. So what I want to do is take that reference angle of 77 degrees and put that in quadrant 3. So if this angle here is 77 degrees, then the whole entire angle all the way around is 180 plus 77, which is 257. And I can check that. If I do the cosine of 257, I should get negative 0.4. 180 plus 77, let's start there. Maybe I did that wrong. 257. So what's wrong with the cosine of 257? Well, the only issue here, now that I've paused and found it, the only issue is that your teacher's a moron. If this right here is 113, if this is 113, then this should be 67, which makes this 67, which makes this not 157 but 147. So if I do the cosine of 147, hopefully that gives me the 0.4 that I'm looking for, negative 0.4. Cosine of 247, Cosine of the non-moronic 247. There's my negative 0.4. Holy cow, that should not have taken so long. I'm sorry. Theta is 247 degrees. So hopefully what wasn't lost in there was that quadrant 3 tells you that your cosine is negative and your sine is negative, which means your tangent will be positive. So I had to make sure that this is a negative here that kind of got lost. My sines are negative, my cosines are negative, my tangents are positive. I found my theta, which required some reference angle and some playing a little bit, but it was there for me, and that takes care of those ones. Lastly, I want to find the length of this arc. Well, here's an angle measure in radians. The nice thing about finding arc length, we call it S, I don't know why, it's just your radius times theta. So all I have to do is 6 pi over 5 times 9, and it's 54 pi over 5, which isn't a very useful answer, so it's going to be somewhere around 30, higher than 30, getting closer to 40 actually. 54 pi divided by 5, 33.9. We would call it 33.9 units, whatever those units were. If you have any questions, and I'm sure you do, because I taught that like a moron, let me know.